As I said, we're gonna be learning about shift-based and shift-based complexes again, but this time around we are going to learn about different types of compounds. Yeah. So the shift bases that you see here is the same shift bases containing serial bond N, but with different source of amine. So we change the source of amine here. So we choose shift base because we believe is a good pharmacophore. So is with the presence of serial bond N, it will help us a lot in the biological activities later. And we know that it's very simple and facile preparation. It's very simple and facile, easy to prepare, meaning when you have shift base, it's easy for you to complex a shift base with any metal ions. And it has been proven so for so many years, in so many applications. And the ligand also can act as mono, di, and polydentate ligands. So depending on the number of donor atoms that we have here. So can anyone tell me how many donor atoms do we have here in this structure? Can anyone tell me how many donor atoms do we have here? Anyone?
I would like to try, Prof. Doctor.
Yeah, silakan.
There's 4 donor atom since there's 4 O atom in OH.
Okay, 4 oxygen atom in the hydroxyl group. Is that all? Ada lagi?
There's also in nitrogen, but since si N-nya udah berikatan sama C, sepertinya udah nggak bisa ya untuk berikatan. Jadi cuman ada di
Do you think so?
OH sama N.
Di nitrogen itu ada, nitrogen is coming from group 15, yeah? It's coming from group 15 or group 5. So 3 bonded, right? Double bond with carbon and 1 single bond with carbon. One
Oh
single
ya,
bond here. So ada balance tak elektron di sini? Do you think there is a balance of electrons here?
iya, masih ada pasangan elektron bebasnya, jadi bisa
Yeah,
berikatan di tengah.
yeah. So we have 2 more electrons here, or a lone pair of electrons. So these 2 nitrogens also can act as a donor atom. So together we can have 1, 2, 3, 4, 5, 6. 6 donor atoms. That's why I said we can form, or we can have polydentate ligands. Yeah. So we also are inspired to synthesize ship bases because it has been reported that ship bases are very good compounds to be applied in medicinal and pharmaceutical fields. Yeah. Now, in this case, just like the compounds that I've shown you last week, we are going to use aldehyde mainly as our source of compound, yeah, primary amine and aldehyde. Even though we can use ketone, but ketone is very hard to be synthesized with amine. There are reports on ketones, there are reports on ship bases derived from ketone, but it's very hard for us to get, yeah, at least to my humble experience. Now, again, this is the ligand. We want to complex the ligand with metal, as I said. Last week, I've shown you mononuclear complex, so only one metal present. But this week, I would like to introduce to you polynuclear complexes. So we can have 2 dinuclear complex, and then we can have 1, 2, 3, 4. This is called tetranuclear complexes. Yeah. Okay. I've shown you this that we use microwave acid synthesis, especially for polynuclear complexes. If you don't use microwave acid synthesis, if you use reflux alone, then it will take like 72 hours, 3 days straight to get one compound. We think that it is such a waste of energy, time, and also money. So that's why we want to shorten the reaction time. We employ microwave acid synthesis instead. So we can get the products within 10 minutes only. Yeah. I told you about the green chemistry principle. I'm not going to talk further on this. Yeah. But if you have questions later, you can ask me. Now, okay, sorry. I'm not used to be using mouse. Yeah, somehow it's very confusing. Wait, see. Okay. Now, in terms of anti-cancer studies, there are many research reported on the potential of shift bases and shift base complexes as anti-cancer agents or cytotoxic agent or biological active agent. So we are inspired to do something with our compounds, and hence we choose colorectal cancer, CRC, as our prime study. So we would like to see how effective our shipase and shipase complexes to kill, to inhibit, to kink the DNA of the cancer. So if they are able to do something with the cancer cells, so we believe that there is a promising finding that we could work further on. Yeah. So why do we choose sheep-based and sheep-based complexes? Because we believe that they have this cationic character and propensity to undergo hydrolysis and redoxylation. So these will lead to DNA cleavage. So when DNA is disturbed in that sense, so we can have a proper mechanism to be studied. So we need to understand further how the cancer is being killed or kinked or disturbed. Yeah, because when we can stop them from replicating, so we believe that the cancer cells can be, the growth of the cancer cells can be inhibited. So we can do this by direct strand excision or base modification. So that can lengthen, we elongate the structure of the DNA or unwind the structure of the DNA, where eventually we can induce a apoptosis. Yeah, apoptosis where a complete death of the cell. So as I said earlier, we are focusing more on the colorectal cancer because colorectal cancer is one of the dangerous cancer. Yeah, I think if I'm not mistaken, it is ranked third among the cancer. So we believe that it is very significant and important for us to study the type of compounds that can kill this kind of cancer. Okay, see. Okay. We also want to study on DNA binding. DNA binding means we want to see how strong our ligand and metal complexes can bind with DNA. The stronger they can bind with the DNA, the better. So later I will show you the value of the KB, the DNA binding strength. Yeah, we can actually quantitatively tell how strong the binding between our ligand and complexes with our DNA. Okay, we can see we can have a few types, a few mechanisms of binding, few modes of binding rather. We can have covalent binding between the compound and also the DNA. We can have intercalation. We can have groove binding, and we can have also electrostatic interactions. Yeah. So for these are known also as non-covalent binding. So this covalent binding, meaning there is covalent bond between DNA and your compound. And this is non-covalent binding. There is no covalent bond formed, but they are employing different modes like intercalation, electrostatic interactions, and also groove binding. Now, DNA binding studies are essayed to measure the ability of small molecules of protein to interact with DNA. I've told you that. And planar geometry, this is something that I would like to emphasize. Planar geometry structures of metal sulfate provide optimal binding for pi-pi stacking. Now, there are reasons why we use palladium, nickel, and platinum because we want the planarity of the structure. The planarity of the structure of the complexes is very important to us because with that geometry, we can assume or we can predict the mechanism of the DNA binding. We believe the DNA binding, the binding between DNA and our complexes and metal is through intercalation because of this binarity. Now we have few types here. The groove binding complexes bind to minor or major groove of the DNA. There is groove here on the DNA here. And then metallo-intercalator, this is through intercalation, binding via aromatic stacking interaction. When I say stacking, meaning you have aromatic moiety of your complex, and then they are stacking one another, yeah, between metal complexes and DNA. And electrostatic interaction, we can have electrostatic interaction between negatively charged DNA and positively charged residues, yeah. So residues meaning within a protein molecule. So we can have negatively charged and also positively charged. This is just like electrostatic forces that exist between any positive and any negative charge that you have learned before. So the same concept can be applied in DNA binding. Sorry. Okay, why we do this? Because cisplatin and who knows cisplatin? I think everyone knows what cisplatin is, right? Anyone? Anyone? Do you know what cisplatin is? Yes?
Oh,
Ada.
ya, dokter, untuk cisplatin itu yang eh, a- atom pusatnya, ion senternya itu dia PT platinum, tapi berikatan sama klorin dan nitrogen NH3.
Ya, yang
Gitu.
amonia. Correct.
Ya.
Ya, betul. Jadi itu cisplatin. Jadi that was the first coordination compound that was tested against cancer cells. Well, it happened accidentally. Ya, maksudnya the scientists then just tried their luck and then test against first on the bacteria, if I'm mistaken, and they tested later on the cancer cells, and it worked wonderfully. And until now, cisplatin is still being used as one of the chemotherapeutic agents. But yet, they come with side effects, negative side effects, which is something that we don't want to have in our compounds. So that's why we try to synthesize new metal-based complexes, hoping that it will not bring the same side effects. And it is definitely cheaper because cisplatin is made up of platinum. Platinum is very expensive, and we're trying to use the same group. Yeah, palladium and nickel are coming from the same group of platinum, but they are cheaper. And then we believe that the work reported on polynuclear sheet bases is still scarce, so that's why we want to have more studies on this kind of complexes. And conventional methods give low to medium product yield, so that's why we use microwave synthesis to increase the yield. At the same time, we can save up time and also energy. Yeah. Okay, we have few objectives. We can have the resynthesis first of the sheet bases and ligands and also complexes, and we characterize this sheet bases using few analytical methods and also physical chemical analysis, such as melting point, molar conductivity, IR spectroscopy, proton NMR and carbon-13 NMR, UV-based, we run TG analysis, powder XRD, and also PSM media analysis. So we want to screen the anti-cancer activities of the sheet bases and their palladium and nickel-2 mononuclear to screen against colorectal carcinoma cell line, HCT 116 via SRB assay. And last but not least, we want to determine the binding strength and mode of interaction of sheet bases with our and also with our palladium and nickel complexes. So we use ctDNA as our DNA here. And there are two methods. We use UVV titration and also circular dichroism method. Yeah, okay, I skip this one and also this one. Now, based on literature review, you can see that we can have metals like zinc, copper, chromium, nickel, manganese, samarium, and then we have cobalt, zirconium, and then we have vanadium, yeah, and so on and so forth. So these are the metals that have been used before to um, in many biological applications. Yeah, for example, they are good as antimicrobial agent, anti-cancer agent, or anti-tumor agent. Yeah, so we compile all these studies just to compare our complexes against these complexes. So we believe that the potential that have been shown by these complexes can propel us further in studying our complexes. Yeah. So these are the ligands used, you can see. Um, and then we have nickel tetranuclear complexes, which has been reported to have a good DNA binding with the DNA. And we have zinc, dinuclear, and tetranuclear complexes, which have a very good antibacterial activities. We have palladium and platinum tetranuclear complexes, also have good anti-cancer activities. And we have zinc, dinuclear, and zinc, and also I think this is cadmium, dinuclear complexes as antibacterial agents. So you can see from here that many reports, many works have been done to study the biological properties, be it anti-cancer, be it antibacterial, of the complexes against various strains of bacteria or various type of cancer. Yeah, the study is there. So we would like to know more about the polynuclear complexes and how well it can or how effective it can be against human colorectal colon cancer cell line. Yeah. So you can see these are some reports on the mononuclear, trinuclear, and dinuclear complexes on HCT116. We can see on HCT116, it gives us about 7 plus 1. I think this is in microgram per mil, 4.1 microgram per mil. Later, I will show you our findings and results. Yeah. Okay. Methodology, we have synthesis ligands, as I said, physical chemical properties, spectroscopic analysis, antigen studies, and DNA binding. Okay, these are the objective of our study. This is the synthesis. I've shown you the synthesis before this, am I right? So this is the microwave that we use. It is known as this is known as monowave for 50. Yeah. So we use aldehyde, and then we use amine here, and then we use ethanol. We get the ligand from the monowave for 50. Yeah. So these are the structure. We can see this is known as OC. Yeah, this one is derived from cyclohexane diamine. This one is derived from phenylene diamine, and this is from PRAN, yeah. Phenylene amine, yeah. This is amine. 1, 2, 3, propylamine, yeah. Okay, so we have 3 different kinds of ligands here. These different kinds of ligand will give you different nuclearity of complexes later. Not all will form all types of complexes. Yeah, I'll show you a bit detailed later. Like this one, for this kind of ligands, we can form mononuclear complexes from OC, and we can form also mononuclear complexes from PRAN. Yeah. Synthesis of mononuclear complexes, the ligand plus the salt of your metal. It can be nickel salt, palladium salt, or palladium or nickel salt. And then we put acetonitrile of palladium. Kalau with palladium, kita guna acetonitrile. Kalau dengan nickel, kita guna ethanol. And then we mix them together, and then we will get the complex here. Yeah, from also monowave 450. Now, these are dinuclear complexes. On the left, you can see dinuclear complexes. From CD, we can get dinuclear complexes. From PD, this is not palladium, yeah? This is PD as in the name that we give to the ligand, yeah? So we have CD, PD, and AD. So we can get also from PD dinuclear complexes here, can you see? And then we can get also dinuclear complexes from AD. From tetranuclear complexes, you can get MPD, you can give us 1, 2, 3, 4 tetranuclear complexes. And from prime, we can get 1, 2, 3, 4 also tetranuclear complexes. Setakat ini okay ke? Ada soalan? There are some parts of the characterization that I will not skip, but I will explain you just a bit because we will be focusing more on the biological activities later. Ya, Haikal atau kawan-kawannya ada soalan? Do you have any questions so far on the structure of the compounds, of the ligands, or the metal complexes? Sebentar ya, saya mau minum air sekejap ya.
Ya, mungkin untuk teman-teman yang lain jika ada pertanyaan terkait yang sebelumnya, baik yang sintesis ataupun metodologi, dipersilakan untuk bertanya.
Ada? Tak ada. Oh, Akbar.
Dokter, mungkin saya ingin bertanya untuk
Ya.
sintesis. From personally, saya belum mengetahui gitu sistematika dari si alat instrumental yang dipergunakan. Kalau nggak salah di monowave ya. Itu tuh ketika si prekursornya, such as acetonitril with pala, pala, with PD
Palladium.
gitu, ya, palladium. What happen gitu ketika kita memasukkan ke si the instrument self? Apakah kalau misalnya di centrifuge kan mungkin diputar. Kalau untuk bagian ini dia di
Tak diputar. Dalam tu we set certain pressure and certain temperature, and we let them in. Kita ada that hole kan, kita masukkan quartz tube, and then we close it, and then after a few minutes we can take it out. So throughout the process sebenarnya kita boleh lihat apa yang berlaku. Ya. There is the interface. There is an interface of the microwave that you can see when the process is taking place. Nanti mungkin kalau ada kesempatan saya rasa saya ada gambar keseluruhan ni. Yeah, but this is just the top of the machine. Yeah.
oh ya.
And yeah, di dalam tu jadi kita campurkan semua sekali, kita tutup, kemudian kita biarkan dalam microwave for 2-5 minutes until we see precipitate form. Yeah. And then we can take it out. But of course, we have to set the pressure and also the temperature first. Boleh?
Oh ya, ya terjawab dokter, terima kasih.
Okay. Sini ada dia. So characterization, we can have many, as I said earlier. For cytotoxicity assay means when we are studying this, when we are screening our complexes against colon cancer cell line, we have few steps taken place. So the first one is called cell culture, followed by cell treatment. And then we are using SRB staining. SRB is actually the dye, yeah. So sulfo-rhodamine B, SRB staining, and step 4, we check the cell viability. So that's how we do this. So we do this together with Prof. Dr. Kalabati from UiTM also. Yeah. So for DNA binding, this is the left, on the left is the UV titration. Yeah, you can see we're using potassium chloride buffer here, placed in the refrigerator, and then the concentration of ctDNA stock solution was determined using UV vis. Yeah, so that's how we do this. So ligand or metal complexes, we mix with DMSO. Apparently, DMSO is our compounds normally soluble in DMSO. Yeah, and then this is 5 millimolar of stock solution. We diluted further. We put in buffer. We diluted further, and we put in buffer, and then we check the UVV spectrum of the reaction between DNA and also our complexes. Yeah, and this is circular dichroism. Yeah, this is circular dichroism that we did. So we have different concentration here: 240, 260, and 80 micromolar. And we put 500 microliter compounds here, and we check using CD. Yeah, this is in collaboration with Dr. Fatima from Aurins from UiTM. So let me give you some results. So ligand and pellet and also complexes. This is the color: orange, green, brown, brown, and green. The way they are green. For palladium and nickel, or it can be brown. But our compounds, the ligands are really orange or bright yellow. And then we can see the melting point here. The melting point increased for higher nuclearity of complexes. We can see also elemental analysis here. Yeah, the reading is quite close with one another. And we have also molar connectivity. Molar connectivity was done to know whether there is a counter ion in your in the compound. So we dissolve our metal complexes, and then we put in certain solvent, and then we test with the molar conductor. So when there is reading, but it's very low. When the reading is very, very high, it indicates that the whole solution of the complexes is having electrolytic nature. So they are electrolytes. So when they are electrolyte, we can tell that they can have probably counter anions, yeah, that present in your compound. So that can be actually indicated through molar conductivity. And this is for PD series, and this is for AD series, yeah. So we did run IR spectroscopy, definitely. Let us see on the shifting of frequency. You can see that for the ligand, CD is the ligand, the blue one. The bottom one is ligand, CD. And then when we form PD and nickel, the mononuclear complex, we can see that there is a slight shifting of frequency. The shifting of frequency means something happened with the bond. So the bond is weakened. Yeah. So when there is a flow of electrons from HOMO of your ligand, of your CD, to empty orbitals of PD and nickel, you must remember that there will be backflow of these electrons, meaning electrons from filled d orbitals of nickel and palladium will be giving back electrons to the LUMO of your ligand. And when that happens, somehow the C-double bond, the bond is weakened. Yeah. So the less electrons you have, the stronger. But the more electrons you have flowing into your LUMO of the ligand, and that will weaken the bond. The weak bonds can be definitely indicated by lower frequency of the IR. So that's how we tell. Yeah. Boleh ya setakat ini? So these are some data, some significant bands of the PD-AD series. Now, next we look at the proto-NMR. You can see proto-NMR here. The most important one, again, is azomethine proton. So for, you can look at this table. Can you see my cursor? I'm moving my cursor now. Can you see my cursor, Haika? Boleh?
Yes, doctor, I can see it.
Okay, so look at the AD. This is the ligand. Is 8.31. Yeah, 8.31 for the ligand. So is singlet with one proton here. When you form complex, the azomethine proton is still there, but somehow the chemical shift is lower, is 7.94. The same things happened for palladium-2 AD. This is dinuclear palladium. It's 797. This indicates that there is a bond between azomethine nitrogen with your metal. If there is bond, then the chemical shift will become lower. Yeah. So the same method, proto-NMR spectroscopy, but for CD series. Yeah, the same observation also observed. And then you can see 1H NMR spectroscopy of PD series. Yeah, PD series here. The same thing also noticed and observed. But not all complexes can be run with an NMR due to solubility problems. Yeah. And this carbon 13, we just want to know how many carbons are there. We want to know how many carbons are there in your compound. Yeah. So you can use carbon 30 NMR. This is nothing new. I know you know this. And UV spectroscopy, we want to know the electron transition. Yeah. It can be from N to pi star, because as I mentioned earlier, we have extra electrons in nitrogen. So those extra electrons can move from N state to pi antibonding state. Yeah. So we can capture this at 438 nanometer. This is molar absorptivity where we calculate through a formula. Yeah. Other than N to pi star, we also want to see pi to pi star of the azomethine or amine. And we also want to see the pi to pi star of the benzene. So those transitions can be captured here. You can see, yeah. So, but when you form complex, you can see N to pi star will become lower in wavelength, yeah. N to pi star for Sirawun N for ligand is 438, but when it forms complexes, it reduces to 403. Yeah. The same thing happened when you form nickel complexes, it reduced to 414. When you form dinuclear complexes, you also reduce to 405 and 412. So this happened. Yeah. Can anyone tell me whether this is what transition is this? When you are using UVVs and there is transition of there is a shifting of wavelength, it become lower and lower. What it is known as? Kita panggil apa? There is a term for that. Remember? Ada yang masih ingat?
Eksitasi elektron dari yang dasar ke keadaan transekstasi. Kemudian kalau setelahnya itu emisi, jadi kembali lagi keadaan dasar dari keadaan tereksitasi.
Ya. Yeah. Ada namanya. Kita ada we can call it a bathochromic or hypsochromic. Pernah dengar term ni? Have you heard these terms?
Yes,
Belum?
dokter, pernah.
Pernah kan? Jadi contohnya upon complexation, you can see this hypsochromic shifting or blue shift to lower wavelength. Yeah, blue shift to lower wavelength. Kalau dia ke higher wavelength, kita panggil dia sebagai red shift. Yeah, remember? So red shift means it's having longer wavelength. Blue shift means it's having lower wavelength. Lower wavelength, blue shift. Higher wavelength, red shift. Yeah. So that's what we notice in the UVs. Oh, sorry. So these are for some other series. Yeah. The GA analysis, we just want to know how many water are there. So we can see that for PDAD, there is one lattice water. For PD2AD, there is two lattice water. For PD4AD, there are four lattice water. Yeah, and I4AD also four lattice water. So that's why we did this. Because when we run elemental analysis, we noticed that the values are not close between theoretical and also experimental. So we suspected that there must be some water inside. So in order to verify that, to validate that, we have to run TGA. And yes, we found these numbers of water molecules in our compound. So these are some TGA analysis for some other series. We have AD, CT. We have AD, CD, and also PD series. We also did run powder XRD here. Yeah, we just want to know the crystallinity of the complexes. So, and the ligands. So we can tell that there are not, if the intensity of the curves of the complexes decreasing, showing decreasing trend, means they are semi-crystalline or amorphous. Yeah. But if they are having moderate degree of crystallinity, we can see that most of the complexes falling within the range between amorphous and crystalline states. Yeah, so that's why we draw this. Kenapa kita buat ni? Because unfortunately, my student did not get the single crystal. So we have to show somehow to the examiner, to people that are reading our paper that, well, even though without single crystal SRT, we can tell the crystallinity of the complexes, something like that. Yeah. Oh, kenapa ke sini? Sorry, di mana tadi kita? Where did we stop?
Powder dan XRD.
Yeah, powder XRD. So kemudian FISAM EDX, yeah. You can see this AD, no complex, and then this is with palladium complex. This is with 2 palladium complex metal, and this is with 4 palladium metal. You can see there is a different in terms of shape of the particle. Yeah, you can see ligand shape block irregular shape. The average particle size is 20 micrometer, but the size is not definite. Yeah, but we can say roughly this is the size. For palladium complexes, the size is becoming nano. So shape is spherical morphology with smooth surface. You can see for palladium complexes, it's getting smoother and smoother. And more importantly, using EDX, we can see that the tetranuclear complexes are having more metal, palladium. Yeah, you can see palladium for mono is 17.85, and then we have 20.95, and the last but not least, we have 2.70. Why is always like this? I'm sorry. Okay. Yeah. And then DNA, ready for DNA? Okay. So for anti-cancer training, for anti-cancer screening, you can see we have CD series here, PD series, and AD series. So CD is the ligand. You look at ligand first. Ligand we have 17.77. PD also ligand 16.94, and we have AD 18.77. Yeah, this is 5-fluorouracil. 5-FU. 5-FU means this is the common drug. This is the positive control. It's 6.15. And the MSO is the vehicle control because we're using the MSO is 19.2. Now you can see ada tak yang lebih rendah daripada 5-fluorouracil? Can you identify? Can you identify anything that is less than um, that is less than 6.15 ada?
Ada ini dokter di PD for AD ya,
PD
2,77
mana?
ya. Terus
Lagi?
ya yang 2,7, terus PD for PD yang 1,39
Betul.
di series.
Yeah. So the lower the IC50 is, the better it is. Yeah. The lower the IC50, the better it is. Meaning we just need low amount of the compound to kill the cancer. Generally, we can say that. Yeah. So the higher it is, the more inactive it is. So there are many inactive compounds also here. When it is more than 100, we consider them as non-active, like palladium CD, nickel CD, palladium 2 CD. Yeah, they are inactive. Nickel 2 PD. Yeah, this is dinuclear complex. They are also non-active. Okay. So we have 5 complexes possess a potency higher than standard drug. Yeah. The ligand itself has some ability to interact with DNA and retarding its growth. Correct. PD, we have phenyl ligand, show better anti-cancer berbanding CD. Yeah. PD, better anti-cancer berbanding CD. Series as it contain more aromatic groups. We found that more aromatic groups better for the ligand to be biologically active. So they can intercalate between stack-based pairs. As I said, remember, I said about pi-pi stacking. And the PD complexes exhibit superior anti-cancer properties berbanding nickel 2 complexes. Yeah. So PD work better than nickel. So we can tell also that tetranuclear complexes reveal highest anti-cancer activity, followed by dinuclear, followed by mononuclear. Yeah. The anti-cancer properties of complexes is increased when the number of nuclearity increase. Lagi banyak metal inside, the better it is. Yeah, something like that. And to strengthen our findings further, we try to run DNA binding through using UV titration. Yeah, when we use UV titration, you can see hypochromism observed at 420 nanometer in AD. Yeah, so 411 in palladium 2 complexes, you can see 411 in palladium 2 complexes, and 361 in nickel 2 complexes. So why this happens? Because due to compounds binding with DNA helix via intercalation. Remember, I told you earlier that it could be intercalation since they are having planar geometry. And after the compounds intercalate to the base pairs of DNA, yeah, the pi antibonding orbital of the intercalated complex could couple with pi orbitals of the base pair. So remember, in your DNA, you have base pair. Siapa yang ingat structure DNA? Ataupun yang tahu, do you have any general knowledge of DNA? Yeah, they have these base pairs. Yeah, base pairs itu boleh ada interaction with the complexes. And what happened? They will decrease the pi-pi antibonding transition energies, hence resulting in hypochromism. So from this UV saturation, we can actually calculate the DNA binding constant. For example, for AD, you see this table? Boleh nampak ya? For AD, the binding constant is 2.14 10 to the power of 5. And then nickel is a bit lower, 1 10 to the power of 5. Yeah. PD 3.3 10 to the power of 5, slightly higher. Nickel AD 2.5 10 to the power of 5. Yeah. PD2AD 1.1 10 to the power of 6. So you can see that they are having we can say moderate binding strength, because I think in the literature we can have more than 10 to the power of 5, it can be 10 to the power of 6 or 7. Yeah. So there will be some ways we will look into this, and we will increase the binding strength in the future. To know, probably we can play around with the structure of the complexes. Yeah. Okay. Wait. So these are some binding parameters and details on the effect of ctDNA on the ship-based compounds. Yeah. Okay, for some other compounds, yeah. Now, next, we also would like to study on the the DNA binding through CD, yes, circular dichroism for AD2 series. You can see here, positive band near 276 nanometer due to pi-pi base stacking. So this can be indicated through the wavelength at 276, yeah, the positive band. Positive means AP on the positive side, yeah. The negative band near 245 due to helicity of DNA. This band is sensitive to the binding of small molecule, meaning when there is a binding between small molecule with the DNA, this band will show. Yeah. Simple groove binder and electrostatic interaction show less or no perturbation on the base stacking and helicity. Remember, earlier I told you there are a few mechanisms to bind with DNA. It can be groove binding, it can be uh, covalent bonding, can be intercalation. So we can say that for and also electrostatic interaction. So for group binder electrostatic interaction, there are no perturbation on the base stacking and helicity, while intercalation decrease or increase the intensity of positive and negative bands. So we can say that it could be through intercalation. Yeah. Okay. Conclusion is this. Yeah. So based on characterization, we can tell that we can get nickel and palladium 2 with different nuclearity, mononuclear, dinuclear, tetranuclear, and then they can be successfully synthesized via microwave acetosynthesis. The model is known as monowave 450. And then based on the spectral analysis, we can see that there is coordination between oxygen and nitrogen with our metal ion. When we screen the compounds against human colon cancer cells, we can see that tetranuclear is having the highest effective potency than the rest of the compounds. And through DNA binding study also, we can tell that ligands and complexes significantly interact with DNA through intercalation. Yeah, I think that should be that. So as for now, I open for questions and answer. If any, Haikal?
Ya, oke, dokter. Thank you for the explanation. Terima kasih tadi atas penjelasannya. Mungkin kepada teman-teman dan rekan kita sekalian yang ingin bertanya terkait materi ini tentang bioaktivitas atau mungkin sintesisnya juga atau metodologinya juga dipersilakan. Mungkin kalau untuk saya pribadi belum
Yeah.
ada dokter karena the topic itself too advance, jadi harus belajar lagi, learn more lagi.
mm, okay, kalau lain-lain, you learn about biological activities, yeah, of organometallic compound sudah. Have you
Sudah,
learned? Ya, sudah belajar biological activities of organometallic compounds
eh,
sebelumnya? Ya.
sudah Prof, sudah dokter terutama di bagian yang sebagai apa ya, oksida dismutase gitu. Jadi kayak yang radikal bebas dalam tubuh itu bisa didismut
Ah,
itu with organometal.
ya. Menarik. Ini ada beberapa we have few courses. We have inorganic, basic inorganic chemistry, we have advanced inorganic chemistry, and we have also organometallic chemistry. So in advanced inorganic chemistry, these biological activities of the compounds will actually are being taught to the students. But for organometallic, I didn't touch much on the um, biological studies, but we did catalysis more. Ya,
Mung-
ada um,
eh,
uh, soalan
Mungkin
di kelas.
sam- belum ada. Saya izin bertanya untuk yang tadi, dokter terkait si monowave yang
Ya,
yang katanya mau ada apa namanya? Kemol didetailkan terkait the system itself, kayak alat alat yang keseluruhannya.
Ya, sebentar
Oke,
saya tengok. Kalau ada gambar penuhnya ya.
ya.
Oh
Sambil
no.
menunggu yang lain jika ingin ada yang ditanyakan.
Bu Yusi tak ada hari ini ya?
Bu Yusi ada, namun lagi ada kerjaan di yang lain dulu. Dokter jadi mungkin akan menyusul kalau sudah selesai ke sini.
Bentar, saya tunjuk gambarnya ya. Saya share di sini. Share di sini. Oke, saya share. Saya sudah share di dalam chat ya. Kejap. That is the monowave 450. Ya, terus you can
Oh,
see that yang di atas tu kita ada uh, di depan tu kita boleh tengok temperature and pressure-nya, or in fact we can see what happens during the reaction, yeah, inside the quartz tube. You know, the quartz tube is very very strong. The quartz tube, we close it with a cap and put it inside for a few minutes at certain pressure and temperature. Then you can see the precipitate form at the end of the reaction. Yeah. Before this, we use normal reflux. That also can be done. There's nothing wrong using it. Cumanya masanya lebih panjang yang berbanding yang ini.
oh,
Assalamualaikum, Aduh,
Waalaikumsalam.
aduh, maaf ini kayak ada overlap kerjaan. Iya, terima kasih ya atas ininya apa lecture-nya yang sangat menarik dan sangat lengkap. PowerPoint-nya lengkap sekali dari from the first lecture ya until now. Thank you very much.
Yeah,
Uh,
welcome. You're welcome.
ya, Dr. Syahrul, kalau tadi saya tuh sempat menyimak sedikit ya, tapi agak terganggu gitu. Untuk shift base ligannya sendiri, itu sebetulnya sudah punya activity ya, activity anti kansernya gitu ya.
Ya, sudah.
Mhm.
Ya.
Nah,
Ya.
kemudian ketika di apa komplekskan dengan platinum ya, platinum,
Palladium dan nickel.
palladium, oke, sorry, palladium activity-nya meningkat ya,
Ya, meningkat. Ya, lebih banyak.
dibandingkan dengan free ligand ya.
Betul, banding free ligand. Correct.
Berarti di situ ada apa activity ganda mungkin ya dari palladiumnya sama shift base-nya juga ya.
Ya, benar. Jadi, there are many factors affecting the result. Saya percaya because of the planarity. When they form square planar complexes, jadi aktivitinya jadi lebih bagus kerana ada intercalation. Jadi when they bind with DNA, it binds properly. So kalau ligand dia structure-nya mungkin tidak perfectly planar, tidak perfect kerana tidak ada yang mengikat structure itu kan. Jadi saya rasa with the presence of metal, structure-nya lebih planar dan maka intercalation-nya lebih kuat.
Oh iya begitu ya. Dari structure-nya lebih planar ya.
Ya,
Oke,
lebih
oke.
planar.
Mhm. Ya, ya
Sebab
sejauh ini mungkin
ya,
Ya, student itu belum pernah lihat ya yang apa yang tadi dipresentasikan oleh Dr. Shahrul, karena memang penelitian bioinorganic ini belum sampai ke anti cancer juga. Jadi baru ke antioksidan gitu.
Antioksidan ya.
Sama
Saya juga
ya
baru
antioksidan.
buat antioksidan, tapi masih belum.
Mhm.
InsyaAllah semester ini baru ada seorang student yang akan buat antioksidan. Juga
Ah,
menarik juga untuk buat antioksidan. Sebenarnya my ambition is my wish is to have all types of biological activities. Maksudnya
mhm.
ada antioksidan, ada
Ya,
antibakteria, ada anti cancer, semuanya.
ya.
Antioksidan itu biasanya saya buat dengan lecturer daripada food technology.
Mhm,
So because most of them are doing antioxidant properties of their food product, something like that kan, because it's important for them to know. But
mhm.
if we can see, kalau kita sudah boleh buat antioksidan, jadi boleh terkait dengan free radical kan, free radical of the,
Ya.
jadi that's very interesting. And kalau buat
Mhm.
cosmetic chemistry pun, the antioxidant properties of the compound is very important. Yeah.
Ya, ya, ya betul. Yang ini apa kompleks base yang netral, bukan netral sih, ada gugus metoksinya ya. Yang EUK, do you know the EUK 13 134 134 EUK eukaryon,
Yeah.
that that's manganese complex with saline
Oh, mengenai
with
topik itu.
saline. Ya, itu digunakan di kosmetik di Swedia. Di Swedia apa Swiss ya? Lupa saya.
Ya.
EUK 134 itu.
Namanya apa? Manganese ya? Manganese silent ya? AU,
Manganese saline.
is it AK134?
134 ya, 134. Saya kok lupa aja ya
Iya,
nama kosmetik.
ya, iya. So
Nah,
ini
itu sudah digunakan di
silent ya.
kosmetik itu.
EUK ya 134. Ini manganese silent daripada N-acetyl cysteine ya. Oke.
Nah, itu. Ya, nah itu salah satu kompleks manganis salen yang digunakan di cosmetics. Namanya ordinary kosmetiknya ordinary.
Oh, jadi mungkin kerana antioksidan propertiesnya ya.
Ya, itu karena antioksidan propertiesnya yang bagus dan mungkin sintesisnya juga kan mudah ya, mudah
Ya.
gitu, manganis gitu. Terus tadi saya sebenarnya dari pekan kemarin itu tertarik dengan itu ya, saya belum pernah lihat alat microwave yang sintetik untuk sintesis
Oh, oke.
microwave-nya.
Saya
Iya,
sudah kasih
tadi
di chat sih.
alatnya itu seperti apa? Tadi ada lubang-lubangnya itu ya,
Ya, ada di chat. Saya sudah diletakkan di chat box Zoom ini.
di chat box ya.
Uh-uh.
Oke, oke. Ya. Oh iya, like this. Dan dalamnya itu ada eh,
Ada
masing-masing.
lubang-lubangnya, jadi kita boleh isi yang misalkan 12 to 15 quarts tube nya letak dalam tu, and then kita set temperature and pressure, and
Mhm.
system is enclosed system kan. Kalau kita guna reflux,
Iya.
the heat will be tidak homogeneous. Kalau dalam ini jadi
Mhm.
heatnya di semua tube itu mendapat heat yang sama. So jadi
Iya.
feel-nya dan juga purity-nya semakin baik alhamdulillah dengan menggunakan
Mhm.
microwave. Dan paling
Iya,
penting
iya.
masanya lebih singkat. Kalau dulu tetranuclear complexes kita boleh dapat tiga hari,
Mhm.
sekarang 45 minit sudah boleh dapat tetranuclear complex ya.
Iya betul. Mahasiswa TA saya juga sekarang ya masih pakai konvensional ya. Alatnya ya 3 hari.
Yang ya kan 3 hari. Jadi
Iya.
kadang-kadang selain pada tenaga masa, kita pun di sini sukar untuk stay di lab ya.
Hmm.
Jadi selepas jam 5 kena keluar, kena tutup everything. So
Iya.
it's not easy untuk buat reaction yang panjang. Tetapi certain reaction seperti Sonogashira yang saya buat, yang itu untuk katalisis, yang itu biasanya 12 jam. Paling sekejap 12 jam. Baru boleh
Oh,
nampak hasilnya. Yang itu tak, tapi kalau kita guna microwave, probably it will be shorter. Tapi saya belum pernah cuba. Kerana kalau kita ada catalyst, sonograph Shira dan juga menggunakan microwave, so saya yakin akan jauh lebih cepat. Ya. Kalau hack Suzuki tu dia jadi 2 saat macam tu, jadi 10 saat saja. Sudah.
iya, iya. Ya itu kan tidak belum memungkinkan ya untuk microwave yang reaksi katalisis belum memungkinkan ya mungkin ya
Boleh
karena
boleh dibuat, cuma saya belum cuba kerana
oh
saya sedang observe the properties, the catalytic properties of the compound, of the complexes. Jadi kalau kita if I use microwave, jadinya terlalu singkat, belum sempat untuk tengok propertiesnya bagaimana kan. Jadi saya tak,
iya betul betul
ya belum cuba lagi.
iya iya. Tapi kan ada perubahan bilangan oksidasi apa valence number juga ya di situ ya
Ya, ya.
bilangan oksidasinya iya.
Ya, oxidation number. Kalau katalisis, ya. Saya kalau ada di mana di if your university or department ada yang expert in kinetic. So I'm looking for kinetic people untuk tolong the kinetic to study the kinetic properties of the compound, because yang itu saya belum pandai lagi. Jadi saya kena belajar on how to study the kinetic properties of the compounds. Ya, kalau ada rakan-rakan yang boleh bantu nanti ya.
Oke. Satu pertanyaan lagi, Dokter. Minggu kemarin itu kan menjelaskan Sonogashira ya,
Ya,
Sonogashira reaction itu, tapi free copper ya, free copper ya.
betul.
Em, kenapa tidak digunakan copper juga di situ? Kenapa pakai free copper ya?
Ya. Alasan utamanya kerana we don't want to have any contamination in the product. So katakan kita mau we want to have diphenyl acetylene as the product, and then kalau kita menggunakan copper, probably kita akan dapat something else. Kita akan dapat something else. The presence of copper, dia guna copper 1 copper 2 as co-catalyst selain pada PD akan menyebabkan homocoupling. So homocoupling of the reaction. Katakan kita ada reaktan A dan reaktan B, kita mahu dua-dua ini bergabung. But if you are using copper as co-catalyst, nanti A akan bergabung dengan A juga, B akan bergabung dengan B juga. So something like that. So kita tak nak ada homocoupling yang macam tu. So that's why kita try to avoid copper. Tetapi it's very challenging because normally people will use copper in Sonogashira. Tapi because it was my work for PhD, jadi kena ada satu novelty lain, jadi kita kena remove copper from the reaction. But it was challenging, tapi alhamdulillah berhasil mendapatkan produknya dalam masa yang singkat, alhamdulillah juga.
Ya, bagus ya produknya. Banyak hasilnya. Oke.
Ya, alhamdulillah.
Alhamdulillah ya. Baik, Dr. Shahrul. Ya, mungkin itu aja pertanyaannya. Mahasiswa, apakah ada yang mau bertanya lebih lanjut kepada Dr. Shahrul?
Ini kuliahnya online semuanya ataupun ada yang di kelas? Ya.
Ada yang di kelas. Kalau hari ini dan minggu kemarin itu semuanya online.
Oh, semuanya online. Oke.
Ya. Tapi kalau tidak lecture series dengan dosen asing di kelas itunya apa lecture-nya.
Oke.
Ya mungkin tidak ada yang ingin bertanya. Dr. Shahrul, nanti saya minta tolong ya untuk evaluasi bisa memberikan beberapa pertanyaan gitu kepada mahasiswa dalam bentuk tulisan aja.
Oh ya?
dari semua lecture yang Dr. Syahrul berikan.
Oh maksudnya kena tanya soalan?
Iya, iya betul.
Okey, boleh.
Nah, ya.
Ya. Untuk tiga-tiga lecture ya?
Iya, untuk tiga-tiga lecture. Ya, mungkin sekitar satu lecture boleh 5 questions mungkin.
Boleh.
5 questions enough. Jadi 15 questions. About
Boleh.
15. Ya. Untuk pekan depan nggak apa-apa, Prof. Dokter.
Okey, okey.
Ya. Iya, baik. Kalau sudah tidak ada, Haikal, terima kasih ya sudah mewakili tadi.
Ini semuanya
Ya,
tahun
baik.
akhir ya? Tahun akhir kimia? In the
Oh,
finally? Belum.
belum. Belum. Ini tingkat berapa, Haikal?
Tingkat 3.
Tingkat 3 ya. Baru semester 5 ya. Ya, in five semester.
So they have 8
In
semesters ya?
ya, fifth semester ya.
Okey.
Iya.
Semuanya, student, siswa, semoga berjaya, insyaAllah.
Amin. Terima kasih. Oh iya, ini juga ada beberapa yang dari mahasiswa S2 sebetulnya yang ikut join.
Ya, terima
Eh,
kasih.
Iya.
Harapnya membantu. Yang S2,
Makasih juga.
yang S2 research-nya apa kebanyakannya? What are they doing as their research?
Oh, researchnya apa April? April, researchnya apa April?
Nah, ini ada April dan Salsa.
Ada April, Angel, researchnya apa?
Kalau saya di
Nah,
organik,
Angel.
Organik, ya.
Oh, organik ya. Bikin apa? Buat apa Angel?
mikroenkapsulasi dari ekstrak kulit jeruk nipis
Oh,
untuk eh, terapi adjuvan di kanker payudara MCF7, Ibu.
hmm,
Recapitulation, ya. Oke.
microencapsulation ya. Ya, ya ini beragam sih untuk topik research karena kan bidangnya ada 5 ya. Ada inorganik, fisik, analitik, organik dan biokimia. Gitu. Jadi memang semuanya ada topik di masing-masing.
Oke.
Oke, oke teman-teman terima kasih ya atas kehadirannya semua. Eh, Terima kasih sekali lagi kepada Dr. Shahrul. Semoga di di kesempatan yang akan datang bisa kembali kita apa, mendengarkan lecture-nya Dr. Shahrul.
Insyaallah.
Mungkin bisa bisa melanjutkan kolaborasi dalam lecture ini ya. Ya, baiklah.
Terima kasih atas jemputannya. Thank you Unpad. Terima kasih Bu Yusi.
Iya,
It's
sama
my honor to be
sama
in lecture to
Shahrul.
Alhamdulillah. Terima kasih.
Iya, terima kasih juga. Sama-sama. Ya, baiklah kita akhiri dengan hamdalah ya. Alhamdulillahirrabbilalamin. Saya akhiri kuliah hari ini. Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Ya, terima kasih ya, Dokter.
Terima kasih semuanya.
Terima kasih, Dokter. Terima
Lagi.
kasih.
Terima kasih, Bu.
Ya. Ya, Haikal ya. Terima kasih.